Hello everyone, my name is Raju Kumar Biswas. I am from JNCASR. So the title of my presentation is Modeling Pseudo-ternary phase of Ag2Se for realization of N-type thermoelectrics with high ZT, high figure of merit. So first I will explain the basics about the thermoelectric materials, then I will show some of the results of Ag2Se. Yeah. So as we all know, there are 66% energy is getting wasted as a heat energy. So if we can convert those heat energy to the electrical energy through the mechanism called thermoelectricity. So that heat energy can be originated from thermal power plant, nuclear power plant, and vehicle, etc. This is the present status of thermoelectric figure of merit, where it has been shown, observed that GET, SNT, PBT has been shown to be champion material for thermoelectric applications. The thermoelectric figure of merit can be characterized using this expression, where S is the Seebeck coefficient, sigma is the electrical conductivity, and kappa is the thermal conductivity, and this is the temperature. So thermal conductivity has two contributions. One is from electrical contribution to the thermal conductivity, and another one is the lattice contribution to the thermal conductivity. From this expression, it is clear that the good thermoelectric material should possess high Seebeck coefficient, high electrical conductivity, and low lattice thermal conductivity. In this table, I will show here that metals are not good as a thermoelectric materials because it has very low Seebeck coefficient. So as I already told, if Seebeck coefficient is higher, then thermoelectric figure of merit will be higher. So for metals, since Seebeck coefficient is lower, so metals are not good as a thermoelectric material. Similarly, insulators also not good as a thermoelectric material because it shows very low electrical conductivity. Although it shows very high Seebeck coefficient, but since electrical conductivity is very low for insulators, so it is not suitable for thermoelectric application. In contrast, semiconductors are good for thermoelectric application because it has moderate electrical conductivity, high Seebeck coefficient, and low lattice thermal conductivity. Because of that, semiconductors are mainly used for thermoelectric application. Today, I will be interested mostly in the N-type thermoelectric materials. So it has been observed that the bismuth telluride, lead tellurides, and SNAC are the champion material as a N-type thermoelectric materials. But today, I will be interested only beta phase of Ag2Se. And my motivation will be to reduce the lattice thermal conductivity by increasing the configuration entropy. Similar studies has been already observed, like super lattice of SNT, SNAC, and SNS. The lattice thermal conductivity is reduced for this super lattice from 2 watt per meter Kelvin to 0.5 watt per meter Kelvin at 700 Kelvin. In fact, for PBT, PBSC, and PBS also, they have shown that for this super lattice, thermal conductivity reduced from 1.2 to 0.6 watt per meter Kelvin at 800 Kelvin. And similarly for GET, GESC, and GES also. So my motivation is to see this super lattice, Ag2Se, Ag2TE, and Ag2S. So to validate our theoretical model, we have compared our theoretical calculation with the experimental value. So for our theoretical calculation gives the electrical conductivity is around 2400 Siemens per centimeter inverse for electrical conductivity, and lattice thermal conductivity also we are getting 1.01 watt per meter Kelvin, and experimental value is 0.96 watt per meter Kelvin. And we have also compared our theoretical result for experimentally synthesized 50% tellurium doped Ag2Se at 400 Kelvin, and here also we are getting from our theory 0.74, and experimentally it is around 0.7 to 0.8. So this is the crystal structure of beta phase of Ag2Se. So here two types of silvers are there. So one is distorted tetrahedral and another one is bipyramidal. So it has been observed by the researcher that there is a phase transition from orthorhombic to cubic phase transition at 407 Kelvin. And it has been also observed that cubic phase is not good as a thermoelectric material because it is metallic in nature and superionic characteristics. So we are interested only in the orthorhombic phase, low temperature phase mainly, and it is an orthorhombic crystal structure, and this is the lattice parameter. and it shows the narrow bandgap semiconductor. From the Phonon study, we have shown that this beta phase of Ag2Se is dynamically stable. And this is the computation methodology we have used. So we know that Seebeck coefficient can be written using this expression, and Seebeck coefficient is mainly the first derivative of the density of state with respect to energy. And from this is the mobility expression. It mostly depends upon C3d. It is elastic constant. This is deformation potential constant, inversely proportional to deformation potential constant, and effective mass, inversely proportional to the effective mass. And deformation potential constant is the first derivative of the delta energy. So it is the strain. As we increase the strain, how the band edge is changing, that gives the deformation potential constant. And that elastic constant we can calculate using this expression. So once we know the mobility, we can calculate the electrical conductivity using the Dure formula. And Phonon relaxation time has been calculated using this expression. So 1 by tau is proportional to that phonon scattering state and inversely proportional to the elastic constant. And these are the phonon group velocity, separate k and k prime, separate phonon group velocity, and this is the energy scattering term. So once we know the phonon relaxation term, you can calculate the lattice thermal conductivity using this expression. This is the specific heat, phonon specific heat, and this is the phonon group velocity and the phonon relaxation time. So we can summarize here how it is dependent. So carrier mobility is proportional to the carrier relaxation time, carrier group velocity, but inversely proportional to the carrier effective mass. And carrier relaxation time is inversely proportional to the carrier acoustic phonon scattering strength and carrier scattering strength. But in real material, it has been observed that there are many types of scatterings is there, like charge phonon scattering, charge scattering, charge impurity scattering. So at high temperature, we have considered the carrier phonon scattering is the dominating one, and because of that, we neglect the impurity scattering and boundary scattering in our calculations. Now coming to the result part. This is the electronic band structure of beta phase of Ag2Se. So as we dope the sulfur, it is like 25% sulfur is there. So we can see that band gap is increases because of the sulfur doping. But for tellurium doping, band gap decreases. So we optimize the band gap with the co-dope case. So it is like tellurium and sulfur is there. For this case, band gap we are getting around 0.18 electron volt. So you all know that PB and GGA underestimate the band gap. To get the accurate band gap, we have also calculated the band gap using the HSE functional, 06 functional. So here, for using the HSE 06 functional, we are getting band gap around 0.64 electron volt. And for sulfur doping, it is 0.78 electron volt. And for co-dope case, 0.66 electron volt. Actually, this higher band gap is applicable to reduce bipolar conductivity. In fact, we also observed the Rashba effect for this type of material. So Rashba effect is nothing but the lifting of the spin degeneracy in the momentum space due to the spin orbit coupling. So since there is a heavy metal in the system, so spin orbit coupling is expected, and we observe the Rashba type of effect. So for sulfur doping, there is a splitting of bands, but interestingly for tellurium doping, this is the Rashba effect we observed. And for co-doping case also, we saw the Rashba effect. And spin orbit coupling is mostly coming for this case due to the tellurium doping. So sulfur atom increases the band gap, and tellurium atom split the spin dependent band degeneracy, and it is useful for thermoelectric application. Now the effect of Rashba effect in the density of states or projected density of states. So we see that total density of states, there is a sharp peak for co-dope system near the Fermi level in the N-type case. So this sharp peak in the density of states originated mostly due to the tellurium, which leads to the Rashba effect in the system. This higher density of states effective mass leads to the enhancement in the Seebeck coefficient. As you already know, if there is a sharp peak in the density of states and it is the first derivative of the density of states, so Seebeck coefficient is expected to be very high. And we also observed that for projected density of states that it has a highest contribution from the tellurium orbital near the Fermi level. So from this graph, it is sure that tellurium has the highest contribution to have the Rashba effect. Now here I have shown the Phonon dispersion curve for Ag2Se and for as a sulfur doped, tellurium doped, and co-doped case. So once you optimize the crystal structure, you observe that there is off-centering of the sulfur atom from its original position, and it reduced the energy by 2.03 millielectron volt. So this gives rise to the soft phonon mode in the system. In fact, through the sulfur doping and tellurium doping, we are getting increasing the configuration entropy. So the origin of soft phonon mode and arising the higher configuration entropy leads to the reduction in the lattice thermal conductivity. Here, for this sulfur dope and tellurium and co-doped case, we are getting very exceptionally lower, very soft phonon, soft phonon mode at M point and K point, and this is the signature of the to achieve the low thermal conductivity. Since we are getting very low phonon mode, so we expect that carrier concentration will be limited by the optical phonon mode also. So we have calculated the mobility using this expression. So this is the mobility expression calculation. So for co-doped case, we are getting this is the mobility, and once we know the mobility, we have calculated the electrical conductivity also. And tellurium doping increases the mobility because of the reduced M star and appearance of multiple level near the Fermi level. So here I have shown the Seebeck coefficient as a function of temperature. So Seebeck coefficient for sulfur doped is very high. For tellurium doped, this is the blue color one. So tellurium doping increases the electrical conductivity, and sulfur doping enhances the Seebeck coefficient, and it leads to the higher power factor for this co-doped case. And here I have shown the compare the S-doped, T-doped, and co-doped system, the lattice thermal conductivity. So lattice thermal conductivity obtained using the deformation potential theory based Boltzmann transport equation formalism. So for co-doped case, K reaches the minimum value 0.34 watt per meter Kelvin at 400 Kelvin for co-doped case. So actually, because of the very low lattice thermal conductivity, we are getting ZT 2.1 at 400 Kelvin for co-doped system. So in conclusion, this co-doped is the dynamically and energetically stable system. Rashba effect spin split band dispersion appears due to tellurium, and it introduces the sharp peak in the density of states, and it is effective to enhance the electrical transport. Configuration entropy due to atomic size mismatch actually increases the point defect scattering. That off-center sulfur atom and scattering due to optical mode reduces the mobility, and in turn reduces the effective ZT. And point defect scattering along with off-centering to reduce the lattice thermal conductivity. And because of that, we are getting exceptionally high 2.1 figure of merit at 400 Kelvin for this co-doped system. And this system, 50% tellurium doping is already synthesized. We hope that this also can be synthesized experimentally. With that, I would like to thank my PhD supervisor, Professor Shobhana Kapoti, for his scientific discussion, and JNCASR for postdoctoral fellowship. And I'm thankful to my lab members at JNCASR. Thank you.
We have time for one quick question.
Hello. So, can you hear me?
Yeah, I can hear you.
So at the very first slide, you mentioned that semiconductors, they are good for thermoelectric.
Correct.
Why is that so? Maybe I'm confused. See, you said that electrical conductivity is high for metal insulator. Sorry, metal, it is very high. Thermal conductivity is also very high in metal, but semiconductors, it is moderate and low. So how would that be very good? Of course, Seebeck is high in that sense.
Yeah, for semiconductor, we want to have good thermoelectric material. Seebeck should be higher, electrical conductivity should be higher, simultaneously thermal conductivity should be lower. Okay, so for semiconductor, actually, the Seebeck coefficient higher, thermal conductivity is lower. Because of that, these cases can be exactly matched for semiconductor only.
So for a good thermoelectric material, electrical conductivity and thermal conductivity both should be. Both should be like they don't need to be high, right?
No, that if the electrical conductivity is higher, thermal conductivity has to be lower. If both are higher, then it cannot be high thermoelectric figure of merit. So that is the challenge in thermoelectric material.
Okay, Yeah, thank you. And one more quick question.
Yeah.
How did you choose the dopants?
How we chose the dopant?
Yeah.
Okay, so that is the periodically in same column. You'll find like similar studies. Yeah. So see, if you sorry. Yeah. So if you see similar class of material like SNT, SNAC, SNS, so mostly that these are a chalcogen material. Okay, so in the periodic table, these are all on in column. Okay, so yeah, thank you.
We should probably move on to the next talk. So let's thank the speaker again.